Okay, welcome back. Hope you had a nice break. Trying to think of what we were talking about before. So I believe we were almost there, done with chapter 9. We're very close, I think. So chapter 9 was solutions, I think. Why not? And solutions, just a little bit of reminder where we're talking about. Again, are those homogeneous mixtures. They are the ones that have the aqueous symbol next to it. As we talked about, there are two parts to a solution. There's the solute, which is the smaller part of the solution, and there's the solvent, which is the larger part of the solution. And remember, typically speaking, the solute will dissolve in the solvent. And we talked about some solubilities and the idea of kind of like dissolves like in terms of how solutions sort of mix. Remember that really solutions interact with other solutions the same way that they interact with themselves, and that's going to make them really soluble and mix really well with one another. Remember that though, when we sort of try to mix things that are very different in the way that they interact with each other, which are known as intermolecular forces, we tend to get things that are going to be insoluble in each other. So as we talked about ionic things, which are positive and negative, and polar things, which has a positive and negative sort of side to the molecule, will be really fine in each other. They will mix and everything. Things that are polar and polar, because they both have a dipole moment, they both have a fixed positive side and negative side to that molecule. They'll be able to interact really well with each other, either through dipole-dipole interaction or hydrogen bonding that we talked a little bit about, I think, and also nonpolar things and nonpolar things will also be soluble in each other. Again, nonpolar things use what is referred to as dispersion forces as their main source of how they interact with other molecules. So they will interact with each other the same way. Remember, so these things are typically going to be soluble in each other. Really only problematic in a lot of cases if you take something that you know is polar and something that is non-polar and try to mix them together. They typically will not mix and they will be insoluble in each other. And again, it's because they're really using a wide variety of different sort of interactions. Again, the nonpolar guy is going to be using something like dispersion forces, which is very, very different than polar, which again, as I mentioned, would be using dipole-dipole or hydrogen bonding. We also talked about in this chapter, I think, some concentration type units. And we talked about percent mass to mass, which is the mass of a solute divided by the mass of the solution times 100%. Remember, on this one, we do want to be careful with the bottom part of it because very common in these type of problems, the solvent and solute is given to you separate. So you need to oftentimes add those together to get the mass of the solution so that you're not just using the mass of the solvent. There's also percent volume to volume, which is the volume of solute divided by the volume of solution. I ran out of room there, but times 100% if I squeeze it in there at the end. We also had percent mass to volume we talked about, which is the mass of the solute divided by the volume of solution times 100%. We then talked about these in terms of doing problems. We also talked about it in terms of sometimes it's easier when you're doing problems involving these percent concentrations that you kind of convert it into like a usable conversion factor, and you could assume 100. So again, if you had a 4% by mass solution of sodium chloride, that would mean you have 4 grams of sodium chloride in 100 grams of solution. So you can kind of use that as a conversion factor. We then talked about probably the most common unit of concentration, which is molarity, or big M, which is moles per liter. And you can think of molarity as really like a formula because we do solve for any of these three things. So if you needed liters, that would be moles divided by molarity. And if you needed moles, which is a very common calculation, that is liters times molarity. We also talked about the importance that if you had a 4 molar solution of sodium chloride, when you're doing it in a calculation, a lot of times it's best to kind of do it as a conversion factor and get rid of the big M. And that would be the same as saying there are 4 moles per liter of sodium chloride. That way you can see both units, the moles and the liters part of it, and you hopefully will not forget about one or the other of those units. As I mentioned before last time, it's very common that people will leave the big M in their calculation and really have no clue about where the volume is or what they should be doing with the volume. So again, if you just kind of convert it out into both units, you can see it, and it oftentimes is a lot better. The number always stays with the moles part, and it's always 1 liter. When we do multiply the molarity by the volume, it does need to be in liters for everything to properly cancel out. Let's see here. We also talked about dilution, I think. And dilution is when we add more solvent. And because we add more solvent, the liters of solution here gets larger. And that means the molarity gets smaller. So the molarity goes down because we're adding more solvent to this. There's a dilution equation, which is M1V1 equals M2V2, or more generically, C1V1 equals C2V2. M is molarity, V is volume. On the other one, C is concentration and V is volume. As we talked about, you technically could use any concentration unit in this formula, but a lot of times people use M1V1 equals M2V2 because molarity is kind of the most common unit of concentration that's used. But technically, you could use anything like percent mass to mass and so forth in there. This is the one place where if you want to, you can leave the volume in milliliters as long as it's milliliters on both sides and everything will cancel out correctly, or you can convert it to liters and then you'll just have liters as your volume. So you can leave it in there as long as you're using this equation. But if you are just using molarity by itself, and you want to convert to moles, you need to convert it to liters because you most likely need moles. And if you do not do that, for example, and multiply it by milliliters, you will get millimoles, which is not moles, is about 1,000 factor off of what you probably need. So molarity by itself, standalone sort of calculation, non-dilution situation, always convert the volume to liters when using it with molarity. But again, if you're using dilution equation, you can keep it in milliliters. It'll all work out okay. I think along the way too, I have a vague recollection of electrolytes we talked about, I think, in this chapter as well. Remember, electrolytes are substances that when they go into water will break apart into ions, and it's the presence of those ions which help conduct electricity. There's strong electrolytes which 100% break apart into ions. Nothing stays together. It's just a bunch of ions floating around in the solution. Because there's a lot of ions in the solution, right, it will conduct electricity really well. Light bulb will go off very brightly. We talked about sort of the light bulb example. Weak electrolyte, on the other hand, will actually mainly stay together, but will break apart a little bit. And remember that a weak electrolyte typically has those arrows heading in both directions when you look at the equation, and it will again mainly stay together, but will still break apart into a little bit of ions. So since there's a little bit of ions in the solution, it will still be able to conduct electricity, but again, nowhere near as well as a strong electrolyte. So like the light bulb example would be, it would go off, but it'll be dim. And there's also non-electrolytes, which will dissolve in solution, but will not create any ions. And because it doesn't create any ions, it will not conduct electricity in that particular case. I think we also talked about equivalents, and equivalents are based off of the charge of ions floating around in the solution. So something like this, we could use a conversion factor, 1 mole of sulfate would actually have two equivalents. Remember, it doesn't really matter the charge in terms of positive or negative. When you're doing equivalents, it's really just the number is what you're going to use. And we did some calculations where we calculated like the equivalents per liter or milli equivalents per liter, which is again a common way that sometimes electrolyte solutions concentrations are calculated. And it's sort of calculated based on the charge of the ions that are kind of floating around in that solution. Any questions on any of that stuff there? Yeah. I also think somewhere along the way we did solubility rules. I think I feel like this is in this chapter as well. Any questions on that? Okay. All right. So I think we also talked about osmosis. I think that's sort of where we finished up a little bit. So we just got a couple more slides to go. We're going to talk about a couple other ways to describe solutions here. There's isotonic solution. And isotonic solutions exert the same osmotic pressure as body fluids. Most IVs are isotonic. So what does that mean? It means, for example, if you take like a red blood cell, which is the classic example, and you put it into a isotonic solution, basically the pressure outside of the cell and inside of the cell are going to be basically equal. And the red blood cell is like a semi-permeable membrane. It's going to allow things to flow in and out of the cell. And what you're going to have is sort of nice, equal flowing in and out of the cell. Nothing bad is going to sort of happen in that particular situation. So there are two sort of numbers that are considered sort of isotonic in terms of solutions, and that is 0.9%. I think it's mass to volume there of sodium chloride, or sometimes referred to as a saline solution, and 5% glucose. These are considered isotonic solutions. It doesn't necessarily have to be sodium chloride. It could be some other ionic compound, but sodium chloride is very common. So there's also solutions which are hypotonic, and hypo means less than. And that means that if you take, for example, our red blood cell here, and you put it into a hypotonic solution, that means that the solution outside of the cell is less concentrated than the solution inside the cell. And if you remember, the process of osmosis is things will move, our water molecules will move from an area of lower concentration to an area of higher concentration. The idea there is it's like trying to dilute it down, so everybody's going to flow to the higher concentration. So in this particular case, because the solution is actually lower in concentration, what's going to happen is all the fluid from the solution is going to flow basically into the cell. And the result of that is, as you can see here, the cell will start to swell and possibly burst, which I'm assuming is probably not a good thing. And that is known as hemolysis. And that's what's going to happen just by the process of osmosis, basically. Now, we also could have a hypertonic solution. And in a hypertonic solution, if you put your red blood cell in there, hyper means more than. So hypertonic solution means that the solution outside of the cell in this case is actually going to be more concentrated than inside the cell. So what's going to happen is the process of osmosis is going to occur. But in this case, your cell here is going to go, we need to kind of dilute everything that's outside of me. And basically everything's going to rush out of the cell in an effort to sort of dilute down all the surrounding solution, which is more concentrated. The result of that is we're going to see the cell start to shrink and go through crenation, which also not such a good thing here. So isotonic solutions are typically IV solutions because obviously if you're getting an IV, you probably have some issues. So you don't want to cause any more issues by giving somebody an IV. And here, hypertonic solution, we're going to have basically everything rushing out of the cell to try to dilute everything that's on the outside, and it's going to shrink. And vice versa there. If we have a hypotonic solution, all the solution is going to rush into the cell. The cell is going to open up and let everything in, and it's going to start to swell and burst. Any questions on that there? So those two numbers you should know, 0.9% sodium chloride and 5% glucose, again, is our isotonic type solutions. All right. So here we see isotonic here, nice happy donut. We have our hypotonic solution, jelly donut exploding, and our hypertonic solution, donut hole happening right there. So let's decide what's going to happen here. Will it swell? Will it shrink? Will it go through crenation or hemolysis? If I put a red blood cell in the following solutions, let's throw it in a 1.5% sodium chloride solution, a 2% glucose solution. Let's do a 0.9% sodium chloride solution. Let's do some water, pure water. All right, so for each of these cases, decide, will it shrink, will it swell, will it go through crenation? Okay, so let's take a look. So remember the two numbers that you should know, basically 0.9% sodium chloride and 5% there glucose. And again, these are isotonic, right? So when we look at our red blood cell there in a 1.5 sodium chloride solution, 0.9 is isotonic, so 1.5 is definitely more than, right? So this would be a hypertonic solution. And that means that we would have this situation happening here. That means that, again, the solution outside of the cell is going to be more concentrated. So all the fluids from the cell is going to basically rush out of the cell and start to shrink and go through crenation here. So this is going to shrink and go through crenation. Yeah. Any question on that one there? 2% glucose, so 5% is isotonic. So it is as simple as 2 is less than 5. So that is less than there in that case. That means that this case would mean we have a hypotonic solution occurring here. And that means that outside of the cell is less concentrated than inside. So everybody outside of the cell is going to rush in and again cause it to go through hemolysis there and burst, basically, right? Swell, go through hemolysis. 0.9% sodium chloride, 0.9% is an isotonic solution, which means your cell is going to be okay in this case, right? So we're going to get equal flow inside and outside of the cell. How about pure water? Is it isotonic? Water in this case is not a good thing because water has no osmotic pressure, which means pure water has no osmotic pressure because there's nothing in it, which means this is actually a hypotonic solution. Yeah. And this is a case where water would not be good. Yes. And this is, again, in this case, outside of the cell is going to be less concentrated inside the cell. So all that water is going to rush in and cause it to burst. So again, sometimes people think it's water, can't be harmful. In this case, could be harmful. Yes. Any questions on that there? Okay. So clear, you need to know those cutoffs. Yeah. All right, so dialysis is a process similar to osmosis. It allows small solute molecules, such as ions and solvents, to pass through. But again, it sort of traps larger ones, like a dialysis bag, for example. Again, you can't necessarily see it, but there are kind of small openings in it. And again, it's going to allow certain size molecules to go through, and others are going to get sort of caught. And that's sort of the idea here. Some of these smaller solution particles can flow in and out, but these larger particles are going to be sort of trapped inside the bag in this particular case. Our body, right? We do some dialysis, right, to get rid of some waste products in our body that we don't want. I think you're going to do this experiment maybe this week. I'm not sure. This might be the one up on top where you got a bunch of stuff in the bag, and every so often you're going to test what's in the solution and came out of the bag and what didn't go and what stayed in the bag. Eventually, you'll pop the bag open. But dialysis sometimes is used in laboratories to sort of For example, if you're doing some type of work with a protein that maybe was in the body, has a specific sort of pH sort of environment it usually is done in, you could put your protein in a dialysis bag, put it into a buffered solution that has that pH, and you can sort of equilibrate it, the protein, to the same type of environment and stuff like that. So sometimes in laboratories we use dialysis bags to kind of do those type of things as well. Any questions on that there? And that is chapter 9. There it is. All right. So chapter 10 is the final chapter, not of the season, unfortunately, but it is the final chapter that will involve calculations. And there's plenty of calculations in this chapter, but this will be the final one involving our calculators for the year here, perhaps. So we're going to talk about acids and bases in this chapter. We'll also talk a little bit about equilibrium and Le Chatelier's principle, I think, towards the end of the chapter, if I remember to do it. All right. So let's talk a little bit about acids and bases. So acids in general have a sour taste. Don't taste any acids in the lab, but bases either. They do cause litmus paper to change. So oftentimes we will use litmus paper, for example, in labs to determine if a solution is acidic, basic, or neutral. Typically, you would use a red litmus paper, and you would use a blue litmus paper. And if it turns red, so typically if your litmus paper turns red, that means it's acidic. So a lot of times you would use like a blue litmus paper, touch your solution to it, and it turns red, then you know that solution is acidic. It reacts with certain metals in reactions that we've seen before. For example, like some zinc plus a little hydrochloric acid. This comes in and kicks out the hydrogen, makes a little hydrogen gas, plus some zinc chloride. And a little balancing like we're in chemistry class, I suppose, as well. That is a single replacement reaction, like we talked about when we talk about types of reactions. Remember that what's coming in needs to be more reactive than what it's replacing in order for that reaction to take place. Aqueous acid solutions conduct electricity. There are strong acids. There are weak acids. And that means that they are also strong electrolytes and weak electrolytes, acids. So a strong acid will 100% break apart in a solution, will conduct electricity really, really well. Bases, on the other hand, have a bitter taste. They do feel very slippery. If you ever get it on your hands, you feel like you have a layer. And a lot of soaps are bases. Things like Drano and stuff like that are bases as well. You could go like Home Depot, I think, and just buy straight sodium hydroxide to clear your drain. There's a lot of warnings on those bottles. Or you could just get the liquid polymer, not so many warnings maybe. But they are used for things like that. Bases also change litmus paper basically to blue. So in this case, you would start with a red one. And if your litmus paper, after you touch it, your solution to it turns blue, that means that it is basic. So again, we sometimes will use litmus paper to help us determine if something is acidic or basic. So in general, if this paper turns red or stays red, it's acidic. Or if it turns blue or stays blue, it's basic in most cases. Just like our acids, there are strong bases and also weak bases, which are strong electrolytes and weak electrolytes and can conduct electricity as well. So let's talk a little bit about an acid and sort of the definition of an acid. An acid is a substance that has the ability to produce H plus ions or hydrogen ions in solution. In acid-base chemistry, pretty much H plus, which is the hydrogen ion, and H3O plus, which is the hydronium ion, is pretty much the same thing. So you can interchange H plus and H3O plus both in formulas and also equations as well. I personally use H plus in everything usually. So anywhere I put an H plus, you could put like an H3O plus, and it's the same thing along the way. It basically means the acid part of it. Also in acid-base chemistry, H plus is sometimes referred to as a proton, and that is because hydrogen has one proton, right? And how many electrons? One electron. And neutrons, it has 0. So in order to become positively charged, it has to lose its electron. So that leaves it just a proton. So that's why it's sometimes referred to as a proton. When we talk about the ability to produce H plus in solution, what we're talking about is the ability of a substance to, when it goes for a swim, basically produce free H plus ions floating around in the solution, not attached to anything, just sort of freely floating around in the solution. And that's something that is a acid. There are strong acids, which are strong electrolytes, which 100% break apart into solution. So there's sort of a list of 6 sort of strong acids. So let me put it up there. There's some right there in that list: hydrochloric acid, nitric acid, sulfuric acid, perchloric acid, hydrobromic acid, hydriodic acid. So this list of 6 sort of strong acids is really a good one to know, because frankly, if it's not one of those 6, it's probably a weak acid. It's probably a safe sort of assumption. So these are definitely all strong acids, which, as it says there, will 100% break apart. So again, if you had a hydrochloric acid there, when it's in solution, it is going to 100% break apart into H plus and Cl minus. And that's going to be 100% of what you have. And that is why it is considered a strong acid, because when you dump that in there, it's just going to produce a bunch of H pluses really quickly and some chloride ions. But it's going to be able to produce a lot of very much free H plus really quickly in that solution, and nothing's going to stay together. You won't have any HCl units still together. It's just going to completely fall apart, basically. Same thing there with the example with our nitric acid in solution. If you had like 100 units of nitric acid, you just basically put in there 100 units of H plus floating around freely and a bunch of nitrates floating around freely in that solution. Questions on that there? Now, bases, on the other hand, are substances that basically can produce hydroxide ions in solution. So it's the same idea. It is a substance that, when it goes for a swim, has the ability to produce free floating hydroxide ions in the solution. Is going to make it a base. There are some strong bases like sodium hydroxide, potassium hydroxide. Most of the strong bases will have hydroxide in it. And again, they took down the periodic table for some reason. But if you look at group 1 and group 2 on the periodic table, you got a little lithium, a little sodium, some potassium happening there. I'm on over there to barium and calcium and strontium. So if you sort of go this way in group 1 and 2 on the periodic table, and any of these guys with hydroxide are typically going to be our strong bases. That is because group 1 is the alkali metals, group 2 is the alkaline earth metals, and the word alkaline means basic, pretty much. So a lot of our strong bases come from group 1 and 2: lithium, sodium, potassium, calcium, barium, strontium, together with hydroxide in the actual formula, are going to be strong bases. So if you had a solution like sodium hydroxide, 100% of what you would have in that solution, it's just the ions that are broken apart. So when that would go in, it's going to produce a bunch of sodiums, which is not important for the pH or anything like that, but it will produce a lot of free hydroxide ions floating around. And again, that's going to make it a strong base. There are some weak bases. And for example, probably the most common weak base that you'll come across is NH3, which is ammonia. Ammonia is actually a weak base. And for example, ammonia needs to actually go find a water molecule, and it will actually take an H plus from the water molecule, and it will produce NH4 plus and hydroxide. So it is still a base because it has the ability to produce hydroxide in solution. It is nowhere near as strong of a base as sodium hydroxide, for example, because all sodium hydroxide has to do is just go in for a swim. It's going to break apart. Ammonia's got to go find some water, do a little bit of a reaction to produce the hydroxide. So it's not going to produce as much hydroxide as, say, the sodium hydroxide would in this particular case. Any questions on that there? So let's talk a little bit about the reaction of a strong acid and a strong base. A reaction of any strong acid and strong base will really result in two things. When we react a strong acid and a strong base, as we've talked about previously, we produce a salt and water in this case. Remember that the water comes from the acid and the base, and the salt is an ionic compound, right? And that is obviously H2O in this case. So if we took something like hydrochloric acid, which is a strong acid, and we reacted it with sodium hydroxide, which is a strong base, this, as you should remember, is part of the double displacement category. That's a positive, negative, positive, negative. Positive guys are going to switch partners. And again, the water comes from the H from the acid and the OH from the base. And the salt would be the sodium chloride in this particular case. So there's our water and our salt in this case. The actual fundamental change that's happening is the formation of water in this case. So what happens is basically this guy, which is a strong electrolyte, will break apart into ions when it's in the beaker. The sodium hydroxide will also break apart into ions because it's in the beaker. Water, which is a pure substance, will actually stay together. And then our sodium chloride will also be broken apart. And this is really what's happening when you put both of those things together into a beaker. So if you take the HCl and you take the NaOH and you toss them in, you will get some H plus, some Cl minus, some Na plus, and OH minus happening. And fundamentally, what's going to happen is this chloride on both sides in the sodium on both sides. These are what are referred to as spectator ions. So if you're a spectator, basically what you're doing is watching, right? If you're a spectator, and that's basically what's happening with these ions. They're just hanging out, floating around, having a nice time in the solution. They're really not making anything. They're there to balance out charges, but they're just kind of floating around, really not making anything. And if we get rid of those, that is how we get to really what is happening in this reaction, which is one of the reasons why a reaction takes place, is the formation here of water. So basically what's going to happen is that H plus from the acid, the OH minus from the base are going to come together to make water. The sodium ions and the chloride ions are just going to hang out and still float around and really not do anything in this particular case. That is why when we have a reaction of a strong acid and a strong base, it is sometimes referred to as a neutralization reaction, because essentially you're making water as the overall reaction that is actually taking place here. Any questions on that there? So if I had that guy right there, right? That's what I just did. So what would be the reaction? Let's say if we had, let's say we took phosphoric acid here, and we reacted it with some potassium hydroxide. What would I get on the other side? Let's take a moment and write the result of that. Okay, so this again is a double displacement reaction, positive, negative, positive, negative. If you're not sure, you just want the basic ions to make these things up. So for every acid, the positive ions, always the H plus, is what makes it an acid. And that's phosphate, which is PO4 3 minus. That is potassium, which is +1, and that is hydroxide, which is -1. So remember, we're going to switch partners, and right there is how we get our water. So again, the H plus from the acid, the OH minus from the base, and remember that is H2O. And here we want to put this together, so that is +1 and -3, which means we actually need 3 of these positive ones to give us the proper form of K3PO4. Now, remember that when you write a formula like this in an equation, you want to make sure that you get the proper formulas down first. Now you can balance it. So you want to make sure proper formulas, then balance. So perhaps a 3 here and maybe a 3 there. And I think we might be in business there. 6 H's, 6 H's, 1 of those and 3 of those. So again, the overall reaction that's sort of happening here is really the formation of water in this particular case. This would obviously be our water here, and this guy right here would be our salt, which again is just an ionic compound. Any questions on that there? Yeah. Now, as I mentioned before, we definitely form salt as a result of this. I would say in most cases, your salts here, which are both of these guys are salts. They oftentimes will be soluble. It is possible perhaps to get an insoluble salt, but probably fairly rare. Most of the time, the salts will be soluble and aqueous because they're just kind of floating around, not doing much in these cases. Once again, this is our switch here, positive, negative, H from the acid, OH from the base, our water, again, the K and the NO3 coming together to make our salt. So that is always how you do it. That's essentially how you can figure out what the salt is. Just put your hand over the H, hand over the OH in the base, and what's left, put it together properly, like you're doing nomenclature, and you'll have the right salt formula on the other side. So let's talk about sort of an early definition of an acid and base, and this was the one that was brought by Arrhenius. He did a lot of work with electrolytes, and he described an acid as a substance, again, that's able to produce hydrogen ions in solution. And he described a base as something that is able to produce hydroxide ions in solution as well. As we'll talk about, it's sort of a little bit limited his definition. He did a lot of work with strong electrolytes like hydroxide, where a lot of the bases have hydroxide in it. As I mentioned earlier on an earlier slide, there are weak bases like ammonia that does not have hydroxide in the actual formula, but can produce hydroxide. But he looked at a lot of bases that do have hydroxide in it. Now, a reminder, or just to demonstrate sort of the difference in terms of the H plus versus H3O plus. When you write an equation, for example, of a strong acid like hydrochloric acid, you could describe how it breaks apart in solution by reacting it with water. And if you do react it with water, for example, in your equation, it's going to send the H plus over here. And when you do, that is where you will produce H3O plus and Cl minus. Now, there's nothing wrong with that equation, and a lot of books will show the equation written like that with the water for a strong acid. But you can also just simply write hydrochloric acid breaking apart in solution without including the water in the equation, and you will just get H plus and Cl minus. So without putting the water in the equation, we get H plus. When you do put the water in the equation, you get the H3O plus. These guys, again, are basically the same thing. It's just two different ways to represent really the acid part of the solution. So they are used interchangeably, like I said, in formulas and equations and stuff like that. As I mentioned before, I personally will probably just write equations like this, where we just kind of take the H plus off. But again, a lot of books will include the water with acids, and you'll get that H3O plus that will be formed. So again, it's the same It's basically representing the same thing. Both of those equations are basically representing HCl going for a swim basically into that beaker, and it's going to break apart really into the ions and stuff like that. Alternatively, you would have your HCl and you would have H3O plus and Cl minus instead. Again, same thing basically here. And that is, again, how you would make, for example, a little bit of hydrochloric acid. You could bubble some hydrogen chloride gas in water and it will become aqueous ions. And that's also the difference between HCl with the aqueous symbol. That involves that it is a solution and it is an acid. So most acids will have the aqueous symbol written next to it. And that's how you know you're talking about hydrochloric acid versus hydrogen chloride gas, which is what this guy would be. So you will oftentimes see acids with that little aqueous symbol next to it to indicate that it is the acid version of it and not say the gas version or something like that. So that's also something that you commonly will see. Now, as I mentioned before, that Arrhenius concept was a good sort of move forward in terms of acid and bases. But as I said, it is sort of limited because he did a lot of work with hydroxide. So a more general definition of acid and bases, and one that's used by a lot of people, was sort of developed by two guys named Bronsted and Lowry. And the Bronsted-Lowry definition of an acid base is an acid is a proton donor. So an acid is something that will basically give away an H plus, while a base is something that will accept an H plus, and it will donate an H plus up here. That sort of happens together. So something will act as the acid and give away the H plus, and something will act as the base and accept the H plus. Now, it's really important when you think about the H plus part of it is not just a hydrogen that's being sort of transferred. It does have a positive charge, which means it does affect the overall charge in the thing that loses the H plus, and it affects the charge in the thing accepting the H plus. So you got to take into account the actual charge that's happening here. So for example, if we look at my NH3 that we saw earlier, the water is going to actually send an H plus over here, and it will make NH4 plus and OH minus in this case. We also saw that we could write an acid reacting with water. And in this case, it's going to send the H plus over here and going to make H3O plus and Cl minus. We see a couple of things here. First off, we see an acid and a base. In the top reaction here, the NH3 is accepting the H plus. So the NH3 here is our base. The water is our acid. But in the second one, it is the water accepting the H plus, which means in this case, it is the water that's the base, and the HCl is our acid. Water in this case, as you can see, can act as an acid or a base, and those are things that are known as being amphoteric. So an amphoteric substance is something that can act as an acid or a base. Now, there's also sort of a consequence of the Bronsted-Lowry definition is it actually creates partners on the other side of the arrow. And what I mean by that is if we look at This is our base. That is our acid. This guy over here is related to this guy over here, and that is what is known as the conjugate acid. And this water here is related to the OH over here, and that is what is known as its conjugate base. So sort of the consequence of the Bronsted-Lowry definition is it will actually create partners on opposite sides of the arrow, which are related to each other. And they are related to each other by only a difference of this guy right here. 1 H plus difference is the only difference between those two things. So the base to the conjugate acid has 1 more H plus than it started with. The acid to the conjugate base has 1 less H plus as it does there. Down here on the bottom one, the HCl and the Cl minus are related to each other. That would be the conjugate base. And the water here and our H3O plus are related to each other. That would be the conjugate acid. Once again, the only difference between those two things is that 1 H plus difference between them. Same difference here. The acid to the conjugate base has 1 less H plus. The base to the conjugate acid has 1 more H plus because it basically gained it. Any question on that there? So in the Bronsted-Lowry definition, we always have just regular acid and bases on the left-hand side of the arrow, on the reactant side. And all your conjugate partners, conjugate bases, conjugate acids are on the right-hand side of the arrow. So that's where we find those guys. So right-hand side of the arrow, we find our conjugate guys. Left-hand side of the arrow are regular acid and bases. Any questions on that there? And here is again, a general definition of it. HA is just a generic acid. It could be like HCl, whatever it may be. And again, these two guys are going to be related to each other. The only difference is 1 less H plus. And these two guys here are going to be related to each other. Again, 1 more H plus. In this case, it's going to be this guy sending that H plus over to the water. When the water, again, in this case, accepts the H plus, it gets an extra hydrogen and also a positive charge because of that plus charge that's coming in. When we look at the HA, when it loses the hydrogen, it's left with an A. And when you lose a positive charge, you become 1 more negative. You lost a proton, so you become 1 more negative, and that's how come it ends up at A minus. So the charge aspect of these partners are really important. People always kind of mess up the charge part of it. So you got to make sure that you adjust the charge both at the acid part where he's losing the H plus and also the base part where they're accepting the H plus. Any questions on that there? Again, there's the one that we were just talking about with our HCl and our water here. And again, in this situation, sending the H plus over in this case. All right, let's take a look here. So in this particular case, our H plus coming on over to our water then becomes our hydronium ion and our chloride ion in this particular case. And once again, that hydronium ion is equivalent to basically H plus as well, basically. All right, so I want you to take a moment here for each of these, decide if they are conjugate acid base pairs. So take a moment and decide if each of these or any of these are related to each other, basically. Okay, let's take a look. So hopefully at this point, we know that that right there should be the only difference if these guys are going to be Bronsted-Lowry conjugate acid base pairs. So that's really what we're looking at. So our first one here, HClO4 and ClO4 minus. Really, the difference between these two is an H plus, yeah. And again, you could put the H plus on this guy and you'll end up with HClO4, or you could take the H plus off of this guy and you'll end up with this guy. So that looks good on that one. HCl and ClO minus, the difference here is an H plus, but there also is a difference of an oxygen, right? And since the other one doesn't have an oxygen, that means that these guys would not be partners. Again, it can only be one H plus difference is the only thing for it to be a partner. We take H2PO4 minus and HPO4 2 minus. The difference here is also an H plus. And again, if you put the H plus onto this guy, you get two hydrogens. Plus one minus two is minus one left over, basically. And you end up with that guy, or take it off going that way. So that would be a pair. And our last one here would also be a pair, as the only difference between these two is an H plus in this case. So it looks like everybody but number two was a pair. Any questions on that there? All right, so for each of these, why don't you write the conjugate base? Starting with that, write what the conjugate base formula should be for each of these. Again, we're just really talking about H plus, and most people have the problem of should you put it on or take it off, and that's the question of what you should do. So this is where understanding the relationship between the acid and its conjugate partners come into play. We know that the acid on one side is partner on the other side should be the conjugate base. We also know that the base on one side is partner on the other side should be the conjugate acid. That means in this particular case, we are looking to write the conjugate base, which means we're looking to end up here, which if we just follow this all the way back means that everything that we're looking at should be an acid. And the definition of an acid is something that will donate the H plus. So in this case, we should actually take an H plus off of each of these guys here because we are looking at basically acids. So that means we're going to take off an H plus here, which means we lose one H. And again, we were neutral and we also lost the positive. So we become one more negative in this case. Here we're going to lose an H, which leaves us an S, and we do become one more positive, not one more negative, which would then bring us to S2 minus. Here we're going to lose an H. That leaves us two H's still there. And again, it was neutral, so we'll become one more negative. And lastly, here we'll lose one of the H's there, HSO3, and once again, we will become one more negative. So this is a good way to sort of think about it backwards. If you know you want to write the conjugate acid or conjugate base, you just kind of think about where does that come from, and then you could just follow the Bronsted-Lowry definition and either put on the H plus or take off the H plus. Any questions on that? So we talked about something being amphoteric. So if you had something like this, for example, if I wanted the conjugate acid for that, and I want the conjugate base for that. So take a moment and write the formula for the conjugate acid and the conjugate base, both starting with a little bicarbonate, and see what you come up with. Okay, so let's take a look. We'll start with the conjugate acid. So once again, I'm looking for the conjugate acid, which means if I go backwards, that means what I'm starting with in this case is a base, which means it should accept the H plus. So we would actually add an H plus to this guy. And if we do that, we'll end up with H2CO3. Again, +1 -1 there, right, will equal 0. Now, if I want the conjugate base, much like the problem, that means in this case, this guy is going to act as an acid, which means he's going to get rid of an H plus basically. And then we will end up with CO3 and one more negative, which would be carbonate. So a lot of things that can be amphoteric or act as an acid and base. A lot of things that have an H and a minus, a lot of times have the ability to do that. That's because they have the H to give, and they also have, with the minus, the ability to sort of accept that H plus coming in on the other way. Question on acid conjugate base pairs. So again, only one H plus difference should be the only thing that's the difference between those two things. When we look at something, say like H2SO4 and SO4 2 minus, are these guys pairs? These guys are not pairs because the difference here is 2 H pluses. So these would not be pairs. And something like sulfuric acid is actually what is referred to as a diprotic acid. And hydrogens basically come off one at a time. So something that's diprotic means it does have two hydrogens it could give, but it will give it basically one at a time. So what will actually happen in this particular case is the H2SO4 will first lose one hydrogen and make HSO4 minus. And then the HSO4 minus will then lose a second hydrogen and make sulfate. Yeah. That is why when we look at partners, H2SO4 and HSO4 minus, they are partners. The only difference is one H plus. That's also why HSO4 and SO4 2 minus are also partners, because the difference there is just one H plus. But when we try to go from here to here, they are not partners because that's two steps down the road. And even though they are related to each other, but they're not related to each other in the sense of a Bronsted-Lowry definition. By the way, is it easier to remove the first hydrogen or the second one? Which one's easier? First one is much easier. After you remove the first one, you now have something that's negative and you want to get rid of something that's positive. So it's going to hold it tighter and it makes it much harder to come off. So really most of the H will come off with the first one. The second one won't lose all that much, but it will come off a little bit. Question on that there. All right, then we'll continue on here with acid strength, I think. So we touched a little bit upon it earlier here. But if the forward reaction in an acid sort of happens, there are some acids which are more weak acids that eventually are products here, can sort of come back together and head in the other direction. And this will give us our arrows that go in both directions, which basically indicate a reversible reaction. Where we have a forward direction going from our reactants to products, and then a reverse direction at some point when our products come back together to make our reactants. These are essentially like our weak electrolytes. They kind of stay together, but some of the products will recombine and come back the other way. It'll eventually reach equilibrium, which basically means that the rate of the forward direction will equal the rate of the reverse direction at some point. You'll have a little bit of everybody probably in that solution. But again, in terms of a weak acid, you will mainly have, this guy still together, not really broken apart. But you will have a few of those ions broken apart, and it's still able to produce some H3O plus, which again is why it's still considered an acid in this case. So if that forward direction predominates with the giant arrow, That means that we definitely have a strong electrolyte and a strong acid, and it's going to be 100% ionized or dissociated. So that is, again, that list of 6 that I put up earlier. That is something like hydrochloric acid, as we've been talking about. Once again, in solution, it's all ions floating around. Pretty much everything over here, 0 over here of this guy still in the solution. And again, as we mentioned, that is why it is considered a strong acid, because essentially it's going to generate a lot of H plus really, really quickly in that solution. And it's going to have the effect on the pH as well. Now, a weak acid, again, you pretty much have the reverse reaction predominating. And what that basically means, it's going to basically keep that weak acid together. So if you had something like hydrofluoric acid, which is a weak acid, when it goes for a swim, it will break apart into H plus and F minus. But in solution, this is mainly what you have. And you have a little bit of these guys. So unlike the HCl, which completely breaks apart, if you have HF, that is mainly what you got floating around. And you got a little bit of F minus and H plus floating around, but a majority of it is still the acids still together. And that, again, is very different than what we see with a strong acid like HCl, where you have none of it still together. It's all completely broken apart basically into ions floating around in that solution. Now, the relationship between sort of acid bases and sort of their conjugate partners is really an opposite relationship. So what I mean by that is, for example, if you have a strong acid or a strong base, their partners on the other side of the arrow, which is conjugate base and its conjugate acid, will be relatively weak. So sort of an opposite relationship. If you have a weak acid and a weak base, its partner on the other side, its conjugate base and its conjugate acid, they will be relatively strong. And what that really means is, and we're not going to go too much into it because it's sort of outside of our class here, but what can happen, for example, is when we have a reaction, say, of a weak acid and a weak base, it can create a salt, as we talked about. And part of that salt that comes from a weak acid or weak base will be relatively strong. And what that means is it has the ability to continue to react actually with water. And it has the ability to go through what's known as a hydrolysis reaction. And it can actually affect the pH of that solution, depending if that's going on. So that's what we mean here when we kind of talk about it being strong. It's not as strong as like a strong acid or strong base, but it's strong enough to continue to react with water and kind of affect the pH of that solution or the acidity or basicness of that solution. So for example, if you had something like HF, right? And as we just talked about, breaks apart into H plus and F minus. And this is our weak acid. And this is its conjugate base. Now, because this comes from a weak acid, this is going to be relatively strong. And something like fluoride has the ability to continue to react with water, which is in the solution to begin with, and actually has the ability to pull off an H plus from water. And it will make some hydrofluoric acid and actually make some hydroxide. And because it's able to actually make hydroxide, it can affect the pH of that solution if you have something like fluoride in there. And that's different than if you had something like hydrochloric acid, which when it breaks apart into H plus and Cl minus, that is a strong acid, and that's its conjugate base. In this case, because this conjugate base comes from a strong acid, the chloride will then not react with the water. So it will not continue to react with the water and do anything to mess up the pH. So the opposite relationship happens because these things come from a weak acid or a weak base. They're relatively strong in the sense that they can continue to react with water, which is in these solutions anyways, because they're aqueous solutions, and it can have effect on the pH. We're not going to get too much into that at all. That's all we're going to get into it, but that's what we mean here when we talk about being relatively strong and stuff like that. It is nowhere near as strong as like a strong acid or a strong base, but it has that ability to continue to affect the acidity of the solution. We have our strong acids in our list that we made before, and we talked about our diprotic acid. There's also a triprotic acid, which is basically like phosphoric acid. And phosphoric acid actually has 3 hydrogens that can come off, and much like sulfuric acid that we saw there at the beginning, they will come off one at a time. So it actually will break apart in a sort of a 3-step process, which, just like the sulfuric acid that we saw earlier, the first hydrogen is going to be the majority of it is going to come off. It gets way harder to take the second one off, and it gets extremely hard to try to pull off that third one at that point, and not very much at all comes off in most cases. But they do lose those hydrogens basically one at a time. So as we talked about, an amphoteric substance is a substance that can act as an acid or base. So as we talked about a little bit earlier, we saw with water, in this case, acting as an acid, and in this case, acting as a base and accepting the H+. Water as well can react with itself, and that's what's happening when you have water in a beaker or whatever. Some waters are acting as acids, other waters are acting as bases. And for example, if this is the acid water, it would send the H+ over here to this water, which is acting as the base, and it will produce H3O+ and OH- in solution. That is what is sometimes referred to as the autoionization of water, basically water reacting with itself. And this is what will determine, as we will talk about, sort of whether or not a solution is acidic, basic, or neutral, is the amount of free of these guys floating around that solution. So this sets up an equilibrium, and with an equilibrium, we could write an important relationship, which is known as Kw. And Kw is the equilibrium constant for water, and it is the concentration of H+ times the concentration of OH-. And when we have the little brackets, once again, that means concentration. And usually what we're talking about is molarity, is usually what we're talking about in that sense. And this equals 1 times 10 to the minus 14. Now, you can think of this as sort of a constant value. The real answer is it does change with temperature, but in most cases, that's pretty constant of a number that you could use, which is 1 times 10 to the minus 14. So this is Kw. This is also Kw. This is one of those formulas like we talked about that you could switch out the H+ for H3O+, and OH- will equal 1 times 10 to the minus 14. This is basically the acid part, and that's the base part of the solution. Same thing here. That's our acid part of the solution, and that's really like the base part of the solution. This is a formula that we could use to calculate either the H+ concentration or the OH- concentration if you're given one or the other. And we could actually compare the concentrations to this time, determine whether or not our solution will be acidic, basic, or neutral. And to do that, if you calculate the H+ concentration and it is larger than the OH- concentration, so the acid part of the solution is bigger than the basic part of the solution, then the solution will be acidic. If you calculate that the OH- concentration is larger than the H+ concentration, the basic part of the solution is larger than the H+ concentration, or the acid part, then it will be basic. If they equal each other, they both will have a value of 1 times 10 to the minus 7, and that would be a neutral solution. This is where Kw comes into play. So Kw is H+ times OH- equals 1 times 10 to the minus 14. The nice thing is it's really the same calculation regardless of which one you're given. You basically take 1 times 10 to the minus 14 and divide it by the concentration given to you. And then you could compare the two and decide, is it acidic, basic, or neutral? The relationship between the H plus concentration and the OH minus concentration is a opposite relationship. So as the H plus concentration goes up, the OH minus concentration goes down, and vice versa. As the OH minus concentration goes up, the H plus concentration goes down. So they run opposites of each other. One increases, the other decreases. I can't tell you how important it is in this chapter, speaking of calculations, that you are using your exponent button, because you will be all over the place as you punch these things in. So make sure you are punching things in scientific notation correctly, and make sure that you're using your exponent button, because out of all the chapters, this is the chapter where it will go bad for you if you are not punching it in correctly. Any questions on that there? All right, so why don't we try these here? These are 4 different problems. So for each of these problems, calculate either the H plus or the OH minus concentration, and then determine if it's acidic, basic, or neutral. Grab your calculator, make sure you know how to punch it in for sure. So 4 separate problems. So this first one, we're looking for the OH minus concentration. This one, we're looking for the OH minus concentration. And these last 2, we're looking for the H plus concentration. And obviously for each of them, is it acidic, basic, or neutral? Again, make sure you use your exponent button. Okay, let's take a look, see how you're doing. So in this case, we do want to use our KW relationship. And like I wrote it wrong there. Not really, but H plus first. H plus times OH minus equals 1 times 10 to the minus 14. Once again, the good news on this is it's really the same calculation regardless of which one you're given. We're going to take 1 times 10 to the minus 14 and divide it by what was given to us. So in this case, for the first one here, our OH minus concentration will equal 1 times 10 to the minus 14, which is the value of KW, divided by the H plus concentration that was given to us. And in this case here, we end up with 2.9 times 10 to the minus 11. We do need molarity on it, as it is a concentration, so you should have a unit that is on that. Again, a reminder that to punch this in properly, that's a 1, that's an exponent button, that's a negative button, and a 14 divided by 3.4 exponent button, negative button, and 4, right? And then hit equals. So again, make sure you are using your exponent button in this case. First off, any question on that calculation there? Now we then want to compare the H plus concentration for this first one to the OH minus concentration. Which one is larger, OH minus or H plus? It is the H plus concentration is larger in this case, and it would be acidic. A reminder that when you look at negative exponents, right, the smaller negative exponent is actually the larger number, because times 10 to the minus 4 means you're only going 4 places this way to put zeros. To the minus 11 means you're going 11 places this way, right, and putting zeros, which makes it a much, much smaller number. So when you're comparing 2 negative exponent numbers, the one that is the smaller negative exponent is actually the larger number, because you technically have less zeros in front of it in that case. Any questions on that there? So again, just to visually see that, our H plus concentration would be 0.00034. Our OH minus concentration would be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. I think 2, 9, something like that, if I counted all the zeros right. So much smaller number again, if you turn it into a decimal place. So smaller negative exponent, larger number, and in this case, it would be acidic. Any questions on that one? All right, let's take a look at the other ones then. Next one is H plus concentration, 2.6 times 10 to the minus 8. That means my OH minus concentration will be our KW divided by H plus, which will be 1 times 10 to the minus 14 divided by 2.6 times 10 to the minus 8. And again, we want to make sure we use our exponent button. 1 exponent negative 14 divided by 2.6 exponent button negative 8. Going to give us a 3.8 times 10 to the minus 7 molar. In this case, the H plus is greater than, equal to, or smaller than the OH minus concentration. It is smaller, right? That's the minus 8. That is the minus 7 in this case. So the OH minus is actually a little bit bigger. And that would make this one basic in this case, right? Yeah. Question on that one. All right, continue on with this one. The next one we had was this, which is our OH minus concentration. Once again, it doesn't matter which one they give you. It really is the same calculation. So in this case, KW divided by the OH minus. Going to give us 1 times 10 to the minus 14 divided by 6.2 times 10 to the minus 9. Once again, want to make sure you punch it in correctly on your calculator. 1 to the negative 14 divided by 6.2 to the negative 9. Going to give us 1.6 times 10 to the minus 6 molar in this case. In this case, when comparing our H plus to our OH minus, that is to the minus 6, which is a larger number than to the minus 9, which means our H plus is bigger in this case. That means that there's more acidic, this solution. Yeah. Question on that calculation there. Last one given to us here, I think, was this one. And again, going to be the same thing. Our H plus concentration will equal our KW, which is 1 times 10 to the minus 14, divided by 8.1 times 10 to the minus 3. Once again, to punch it in, 1 exponent button, negative button, 14, divide 8.1, exponent button, negative, and 3. Yeah. So again, we punch that in correctly on our calculator. Obviously, if you have one of those calculators that you need to put parentheses around, make sure you do that as well. Looks like 1.2 to the minus 12 molar in this case. In this case here, it is going to be our H plus being less than our OH minus. OH minus is bigger, which means it should be basic in this case. Yeah. Any questions on any of those calculations there? So once again, always have this number available to you. Yeah, so think of it as a constant, and it is sort of a constant. Let's try another one here. Oh, is that the one we missed? I think it is. I think it's the first one we did. Look, I'm doing this one again. Are these different ones? All right. Let's try this one. Forget about which one is greater. Let's just do what is the OH minus here, and is it acidic, basic? Okay, so again here we're given the H plus, so really our same calculation, our OH minus concentration will equal our KW, which is 1 times 10 to the minus 14, divided by 2.8 times 10 to the minus 5, and that's going to get us here Looks like 3.6 times 10 to the minus 10 molar. That means in this case, it is actually the H plus concentration that is larger, up to the minus 5 to the minus 10, than the OH minus, which means it should be acidic in this case. Yeah. Any questions on that one or KW? Yeah. Later. So if you have one where you need to put brackets around, you got to do it between each number. Otherwise, your calculator will kind of break up the math wrong and stuff like that. Yeah. Yep. Other questions? All right. All right. So I think we'll skip that next example. Let's try it. Let's just do one more time just to make sure calculators work here. How many times? Let's just calculate the OH minus concentration from an H plus concentration. Just make sure. Yeah, technically the temperatures here is not really important for any of the calculations. It's really because KW is what's known as an equilibrium constant, really. And the only thing that really affects the value of the actual equilibrium constant is temperature. So at 25 degrees, the value of KW is 1 times 10 to the minus 14. It actually will change if it's not 25 degrees Celsius. But for our class, you could probably safely assume in every situation it's 25 degrees Celsius, even if it doesn't mention a temperature. But technically speaking, if it wasn't 25 degrees Celsius, the value would actually be slightly different and stuff like that. But it's almost like a constant because in most cases, that's usually the temperature for these type of problems. And again, here 1 times 10 to the minus 5 molar is what you should end up with in this case. And in this case, that would mean that actually the OH minus is larger, right, than the H plus concentration in this case. And this would be basic in this case, yeah. So again, if by some chance you do need to put parentheses. Otherwise, you could probably punch it in if you have that EE button or EXP button without parentheses. Any questions on that there? Yeah. All right, then let's talk about the pH scale. And the pH scale is really a way that we measure acidity. The pH scale runs from 0 to like 7 to 14, which is use the whole screen. So underneath 7 to 0, there's acidic. Above 7 to 14 is basic. And technically speaking, right there, 7 is neutral. And 7 is sort of the center point, if you want to think about it. As you go from 7 towards 0, it is more acidic. As you go from 7 towards 14, it is more basic as you head in that direction. A lot of numbers and stuff like that doesn't really matter. This is the actual formula here. pH is equal to minus the log of the H plus concentration. It's not negative, that's just PowerPoint there. This is, again, one of those formulas where you also can swap out the H plus for the H3O plus. And again, it's the same thing. So whichever way you want to do it, it's the same deal. Now, this formula, along with all the rest of the formulas we're going to talk about in this chapter, depending on the type of calculator you have, as to how you should punch it in. So if you have a display calculator, you punch it in exactly the way it's written, which is you do negative log and then the H plus concentration with your exponent button. If you have a non-display calculator, pretty much this formula and the rest of them, you actually need to start with the concentration or the number, then you need to hit log, and then you need to hit the negative button. So you kind of have to go backwards. If you're not sure what type of calculator you have, hit the log button. And if it says log, congratulations, you have a display calculator. If it says error, congratulations, you have a non-display calculator. So that is how you determine which type of calculator you have. So again, if you hit log and it says log, display calculator, you basically punch this formula and all the rest of them just the way they're written. If you have a non-display calculator, when it says error, when you hit log by itself, then you need to go backwards on all these calculations in terms of how to punch it in to your calculator. Any questions on that there? More fun with calculators. Here we go. No. So why not add some significant figures to everybody's fun, right? So when we calculate something like pH, the number of decimal places in like the pH value should equal the number of significant figures there are in the concentration value. So we are going from significant figures to decimal places. So the number of significant figures there are in the concentration value is how many decimal places, not significant figures, but how many decimal places you should take like the pH to. That's a lot to be said. So let's make sure we understand what I just said. Let's calculate the pH here. And is it acidic, basic, and neutral? And make sure that you get it to the right number of significant figures. So give it a go, see what you come up with. All right, so pH here in this case, and by the way, the name actually tells you what you need. pH means you need the H plus concentration basically to calculate it. Negative log of 1.0 times 10 to the minus 5. So if you have a display calculator, this is probably the way you should punch it in. You should hit the negative button. You should hit your log button. You should hit 1, your exponent button, your negative button, and 5, and hit equals. You have a non-display calculator. I'll try to remember here. You should start with the number, which would be 1, your exponent button, your negative button, and 5. Then you should hit the log button, and then you should hit the negative button to make it positive. Whichever way you do that on your calculator right about now should be staring at you a 5, I hope. Yes. It's like a magic trick. It's just a 5 right there on your calculator like that, staring at you. First off, everybody got that? Yes. If not, again, those would be the 2 ways to punch it in probably properly here. All right. What should the answer be? Should it be 5? Should it be 5.0, 5.00, 5.000000? I feel like that's a lot of zeros, so I'm just going to eliminate that one right now. Which one? How should we give the answer? All right. I think I heard a little bit. I think I've heard now all the answers except for this one. Anybody want to go with this one? There's a lot of zeros. I kind of like it. All right. So what the rule says is we want to look at the concentration, which is here. How many significant figures does this number have? It does have 2, right? Scientific notation. So it has 2 significant figures. 2 significant figures means that when we calculate something like pH, we should end up with 2 decimal places, not significant figures. But we should end up with 2 decimal places, which means it should be 5.00 in this case. So in this case, we're not going significant figures to significant figures. We're going significant figures to decimal places. We will talk about going the opposite way from pH back to the concentration, and the rules follow the same. So you would go from decimal places to significant figures if you're going backwards as well. This would then be acidic, right? As it is less than 7 in this case. Yeah. Question on that one there. This is fun with calculators. Continuing. All right, let's try a couple here to finish it out. Let's go with the pH for each of these. And is it acidic, basic, or neutral? Each of them. See what you come up with. Okay, so since we're getting, and let's take a look. We'll take a look at number 1 here, and we will calculate the pH. Again, negative log of the H plus concentration. So we're going to go negative log 2.1 times 10 to the minus 5. Again, depending on your calculator as to which way you're going to put it in. But regardless of which way you put it in, you should end up with like a 4.68 in this case. Once again, 2 significant figures, 2 decimal places in this case. This is acidic, basic, or neutral, this one? It is acidic. By the way, when you're asked that question, there is only one answer. Cannot be acidic and basic at the same time, although on many exams I have seen it. Yes, I've never seen all three, like it's acidic, basic, and neutral at the same time, but there's just one answer to that, by the way. And we'll talk about why that happens next time. All right, so number 2 here, we want the pH is equal to minus the log of the H plus. Remember, we need the H, that is the OH. So perhaps we should calculate the H plus concentration using a little KW. So our H plus concentration would be 1 times 10 to the minus 14 divided by 5.9 times 10 to the minus 8. That will give us here 1 negative 14 divided by 5.9 to the minus 8. Gonna give us here, we'll call it 1.7 times 10 to the minus 7. And now we could go into our pH minus the log of 1.7 times 10 to the minus 7. If I actually put the number in, that might help, I suppose. There we go. It's going to give us a 6.77 pH actually here. That is, as they say, slightly acidic. Yeah. Again, we're going to go with 7 on the nose as neutral. Yes. Or super, super close to 7. Yeah. It's like 701, 699. It's got to be pretty much 7 to be neutral. And the reason really for that is the concentration of H plus and OH minus will equal 1 times 10 to minus 7, which if you put it into the pH equation is actually a pH of 7. Is actually what neutral actually is. Now, let's just say you maybe didn't notice that was the OH minus concentration and you threw this into your equation here. And you got this number minus the log of 5.9 to the minus 8. And you got something like a 7.23. You didn't calculate pH, obviously, because that's not the H, that's the OH minus. So you did calculate something. You calculated what is known as the POH, which oddly you need the OH minus concentration. You could calculate the POH by taking negative the log of the OH minus concentration. Now, why would that be helpful? Because if you take the pH plus the POH, that equals 14, which means if you'd calculated this, now you could calculate the pH by taking 14 minus 7.23, and now you have your pH. So not all is lost. You're just like 2 slides early. Any questions on that there? All right, we were laid up there for today.